From a spark to a sphere. The universe's grand opening. Everything we see, everything we are, began in a single moment. An impossibly long time ago, the entire universe was contained in a point smaller than an atom. It was incredibly hot and dense. Then, in an event we call the Big Bang, it started to expand. This wasn't an explosion in space. It was the expansion of space itself. From that initial spark, time, the cosmos as we know it, began their journey. If you could have been there, you would have seen the first light of creation flash across the sky. This ancient light, called the cosmic microwave background, can still be detected today. It is a faint, persistent echo of the Big Bang. This transition marked the end of the universe's infancy and the beginning of the long, slow process of building the complex structures we see today, from giant galaxies to our own blue planet. This journey from a singular hot point to a vast, transparent universe is the foundation of our own existence. The hydrogen atoms forged in those first few minutes are the same hydrogen atoms that make up the water in our oceans and in our bodies. The story of Earth is not separate from the story of the universe. It is a direct consequence of it. The cosmic expansion set the stage, and the simple matter it created provided the raw materials. The deep blue of our world is a direct descendant of that initial fiery beginning, a beautiful and complex outcome of the universe's grand unfolding narrative. Yeah, that really is where it all begins. Cosmic forges. How stars cooked the ingredients for Earth. For millions of years after the Big Bang, the universe was dark. The vast clouds of hydrogen, helium, drifted through the expanding space. But they were not perfectly uniform. Tiny variations in density meant some areas had slightly more matter. Gravity, the quiet, persistent force, began to pull on those denser regions. Slowly, it drew the gas into tighter clumps, then tighter still. Clumps grew massive. Pressure and temperature rose at their centers, setting the stage for the first stars to ignite. When a collapsing core got hot and dense enough, nuclear fusion began. Hydrogen atoms fused into helium. That fusion released massive light and heat. A star was born. The first stars were giants, hundreds of times the sun. They burned fast and lived short, brilliant lives. The universe filled with points of light, cosmic engines making heavier elements. These stars were celestial furnaces. Inside their cores, heat and pressure fused helium, carbon, oxygen, then heavier and heavier elements. Carbon, nitrogen, oxygen, silicon, iron, all forged in those giant stars. These elements couldn't be made by the Big Bang. They proved the life cycle of stars. Without stellar forges, the cosmos would have stayed hydrogen and helium, no rocky planets. At the end of their lives, massive stars didn't fade. They exploded, supernovae. Supernovae could briefly outshine a galaxy. Their final blasts scattered heavy elements across space. That dust, enriched with carbon, oxygen, iron, gold, seeded new gas clouds. The deaths of the first stars were a beginning. Cosmic recycling built new stars, new planets, and eventually, us. That's how the elements of our world were forged. A star is born, the sun's dusty cradle and a planetary family. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a new story began. A vast, rotating cloud of gas and dust, enriched by the remnants of long-dead stars, started to collapse under its own gravity. This cloud, known as a solar nebula, contained all the elements necessary for a solar system: hydrogen, helium, iron, silicon, carbon. As the cloud spun faster and faster, like a figure skater pulling in their arms, it flattened into a spinning disk. This rotating structure is called a protoplanetary disk, the birthplace of our sun and its family of planets. At the very center of this swirling disk, most of the material gathered. The pressure and temperature skyrocketed. Gravity squeezed the matter so tightly, the core grew intensely hot. Eventually, the conditions became so extreme that nuclear fusion ignited. Hydrogen atoms began fusing into helium, releasing an immense torrent of energy. Our sun switched on, bathing the surrounding disk in light and heat. This moment marked the birth of our solar system's star. The young sun accounted for over 99% of all the mass in the nebula, its immense gravity holding the rest of the disk in orbit around it. Farther out in the spinning disk, the story of the planets was just beginning. The material was too spread out to form another star. Instead, tiny particles of dust, coated with ice, began to stick together. Think of it like dust bunnies forming under a bed. Through a process called accretion, these small clumps gently collided and merged, gradually growing larger. Pebble-sized, boulder-sized, kilometer-wide bodies called planetesimals. For millions of years, these planetesimals orbited the young sun, crashing into each other in a chaotic, cosmic demolition derby that was also an act of creation. Over time, a few of these growing bodies became dominant. Their gravity was strong enough to sweep up most of the remaining material in their path, clearing out their orbits. In the hotter inner part of the disk, rocky planetesimals came together to form the terrestrial planets: Mercury, Venus, Earth, Mars. These were worlds made of rock and metal, the heavier elements that could withstand the sun's heat. One of these growing spheres, in a zone that was just the right distance from the sun, was destined to become our home. The formation of Earth was a story of countless small pieces coming together to make something grand. And well, that's how our planetary family began. The early Earth was not the tranquil blue planet we know today. It was a hellish and violent place. As it grew by accreting smaller planetesimals, each collision released a huge amount of energy. This constant bombardment, combined with heat from the decay of radioactive elements trapped inside, turned the young planet into a molten ball of rock. The surface was a glowing, roiling ocean of lava, thousands of degrees hot. There was no solid ground, no water, no breathable air. It was a world constantly being reshaped by impacts from space and the churning of its own fiery interior. During this molten phase, a crucial process called differentiation occurred. The heavier materials, primarily iron, sank towards the center of the planet under the pull of gravity. Nickel sank with it. This process formed Earth's dense metallic core. The lighter materials, such as silicates, floated upwards to form the mantle and the crust. The liquid iron outer core would later generate our planet's magnetic field. That magnetic field became a protective shield that defended the atmosphere from the harsh solar wind. The surface of this molten Earth slowly began to cool. A thin, primitive crust started to form, perhaps like the skin that forms on top of cooling pudding. However, this early crust was not stable. It was constantly being broken apart and recycled by volcanic activity and asteroid impacts. Volcanoes were everywhere, spewing hot lava and releasing vast quantities of gases from the planet's interior. This outgassing created Earth's first atmosphere. It was a thick, toxic blanket of steam, carbon dioxide, and nitrogen with almost no oxygen. This early hostile environment was a necessary stage in our planet's development. The intense heat drove the chemical processes that segregated its layers, creating the internal structure that still drives geological activity today. The relentless volcanism released the gases and water vapor that would eventually form our atmosphere and oceans. The violent beginning of Earth was not a sign of chaos, but the formative process that established the fundamental conditions for the planet's long-term stability. It was a baptism by fire, forging a world that would one day be capable of harboring life. In the midst of Earth's chaotic youth, a cataclysmic event took place that would forever alter its destiny. About 4.5 billion years ago, a protoplanet roughly the size of Mars slammed into the still-forming Earth. This object, sometimes called Theia, didn't just graze our planet, it was a glancing but colossal collision. The impact was unimaginably violent, releasing more energy than millions of volcanic eruptions at once. It would have melted both bodies, temporarily turning Earth back into a ball of molten rock and vaporizing a significant portion of its outer layers. This giant impact hypothesis is our leading explanation for how the Moon was formed. The force of the collision blasted a tremendous amount of vaporized rock and molten rock into orbit around Earth. This debris formed a hot, rapidly rotating ring of material, much denser and closer than Saturn's rings. It would have been a spectacular sight in the sky of the young Earth. This ring of debris did not remain scattered for long. Gravity quickly went to work, pulling small, solid particles and molten blobs together. Within a remarkably short period, perhaps only a few hundred years, or 1,000 years, this material coalesced to form a single, large body, the Moon. Initially, the newly formed Moon was much closer to Earth than it is today, perhaps 10 to 20 times closer. It would have appeared huge in the sky, a massive, glowing sphere of still molten rock. Its powerful gravitational pull exerted a tremendous force on Earth, creating enormous tides in the planet's magma oceans. This interaction caused Earth to spin much faster than it does now, with a day possibly lasting only 5 hours or 6 hours. The close proximity also caused the Moon to become tidally locked, meaning the same face has always pointed toward Earth, a feature we still observe today. The presence of the Moon has had a profound and stabilizing influence on our planet. Its gravity acts like a steadying hand, preventing Earth's axis from wobbling wildly. This axial stability is crucial for maintaining a relatively stable climate over long periods, preventing extreme temperature swings that could have made it difficult for complex life to evolve. The Moon's gravity also continues to drive our ocean tides, which mix nutrients and may have played a role in the transition of life from sea to land. The violent collision that created the Moon was a pivotal moment, giving Earth a celestial partner that helped make it a more habitable world. Well, you know, after the formation of the Moon, Earth began a long, slow process of cooling. The surface, no longer a purely molten sea, started to solidify into a dark, volcanic crust. As the planet cooled, the thick, steamy atmosphere began to change. This atmosphere was saturated with water vapor, released from the planet's interior over millions of years. This water, held as a gas in the hot, dense air, was waiting for the right conditions to fall. It was a planet shrouded in a global greenhouse with a sky full of potential rain. The source of Earth's water is a topic of scientific fascination. Much of it likely came from within the planet itself, locked inside minerals and brought to the surface as steam by countless volcanoes. However, another significant contribution may have come from space. During the Late Heavy Bombardment, Earth was pelted by asteroids and comets. Comets, in particular, are like giant, dirty snowballs made of ice and rock. Each impact would have delivered a substantial amount of water, supplementing the water that was already here. As Earth's surface temperature dropped below the boiling point of water, the water vapor began to condense and fall as rain. This was not a gentle shower. It was a torrential, planet-wide deluge that may have lasted for thousands of years. Rain fell on the barren volcanic landscape, and the water began to collect in the lowest-lying basins. Slowly but surely, the first shallow seas and then vast global oceans began to form. The relentless downpour transformed the red-hot world into a water world. The formation of the oceans marked a critical turning point. With vast oceans now covering the planet, the stage was set for the most remarkable chapter in Earth's story, the origin of life. In the warm, shallow waters around deep-sea hydrothermal vents, a rich soup of chemicals existed. Fueled by energy from sunlight or from Earth's interior, simple organic molecules began to form and interact. Over immense stretches of time, some of these molecules developed the extraordinary ability to make copies of themselves. This was the first, tentative step towards life. These early replicators evolved, becoming more complex, and eventually enclosing themselves within protective membranes, forming the first simple cells. For billions of years, life remained simple. The earliest organisms were microbes, single-celled life forms living in the oceans. Some of these early microbes, called cyanobacteria, developed a revolutionary new process: photosynthesis. They learned to use the energy from sunlight to convert carbon dioxide and water into food. As a byproduct of this process, they released a waste gas: oxygen. At first, this oxygen was absorbed by iron dissolved in the oceans, causing it to rust and settle on the seafloor. But eventually, the microbes produced so much oxygen that it saturated the oceans and began to fill the atmosphere. This great oxidation event was a global transformation driven by the smallest of creatures. It was also a planetary catastrophe for the early life forms that had evolved in an oxygen-free world, as oxygen was toxic to them. However, it paved the way for a new kind of metabolism and more complex life. The buildup of oxygen in the atmosphere also led to the formation of the ozone layer, which shields the planet's surface from the sun's harmful ultraviolet radiation. This protection was essential for life to eventually leave the relative safety of the oceans and colonize the land.